Hello, everybody. My name is Sung Jin-ho, one of the organizers. Yeah, I'm happy to announce the beginning of this workshop. I'm very excited, and we'll kick it off with a talk by Mihalis Dafermos on the cosmic censorship conjectures in general relativity, current status, and open problems.
So thanks a lot, Sanjin, and to all the Jan and all the other organizers. So first of all, let me apologize that my talk won't exactly correspond to the title in the following sense that when I gave this title, I really meant this to be a sort of an encyclopedic talk on cosmic censorship conjectures and really sort of overview the current status and of its glory. And I quickly realized that that's now impossible to do in the space of an hour. And there's been so much work on these topics that it would be a little bit crazy to even attempt that, especially after a nice night at a whiskey bar in Edinburgh. So let me be a little bit more modest in that I'll certainly try to introduce these conjectures. Maybe some of the younger people here don't know the story that led to their conjectures. These are conjectures that, in some sense, summarize a certain picture about singularities in general relativity that we hope is true. So I'll try to introduce them from the beginning, not cut out there. But in reality, I'm only going to survey a minor part of the current status, and maybe a part that's not talked about so much, and I think maybe should be talked about a bit more. And I'll leave parts of the story that will appear in other talks in this conference to the speakers of those other talks, who can pass them much better than I can. So with that caveat, let me begin the talk. So somehow the entryway into understanding what the cosmic censorship conjectures are all about is the celebrated Oppenheimer-Snyder collapse. So let me just fall right in to Oppenheimer-Snyder collapse and take the story from there. So this is a famous paper appeared in 1939, Oppenheimer-Snyder. And what this paper studies is the collapse of a homogeneous, strictly symmetric, self-gravitating pulse. So it's we want to study spacetimes that solve the Einstein-Euler system in simplest possible case where there's no pressure. So what do these spacetimes look like? Well, the best thing is to draw a picture, and unfortunately you will not find that picture in this paper, and this is one of the reasons why this paper took so long to be understood. But the picture of those Oppenheimer-Snyder collapsing spacetimes is this Penrose diagram depicted here, and I'll assume of this audience nodding familiarity with such pictures. So what are we to remember from this picture about the spacetime? To remember the following things. So first of all, this spacetime is evolutionary. I'll talk a little more about the language of the Cauchy problem later in the talk. But in any case, it's evolutionary. It evolves from initial data, and the initial data is absolutely impeccable. It's blameless. Can't say anything bad about the initial data because it's regular. It's actually not C infinity because this has a star and the star has a boundary, but okay, it's regular. The topology of the initial data is Euclidean, so topologically it's R3, and it's asymptotically flat in the nicest possible way. Okay, so there's nothing wrong with the initial data. We're not going to find fault in it. Nonetheless, the spacetime has a singularity. So this exemplifies the notion that in general singularities form in evolution from perfectly regular, perfectly nice, impeccable stars. So there's the singularity at r equals 0. And moreover, related to the fact that there's a singularity, there are observers who live for only finite time. Right? And this is the trajectory of such an observer, this green curve. So this is a freely falling observer, a time-like geodesic whose total proper time is infinite, is finite, and it is finite because in finite proper time this observer approaches this singularity. Okay, so very good. So when this was first written down, the solution, of course, I should emphasize that this geometry was not so well understood at the time. But anyway, in any case, when this solution was first talked about, one could reasonably ask the question: could all of this funny properties, singularities, whatever observers that exist for all time, could this all go away upon perturbation? And indeed, this was very much the conventional thinking that it would. And this conventional thinking was spectacularly disproved in this paper, Gravitational Collapse in Spacetime Singularities of Roger Penrose, for which he received the Nobel Prize 2 years ago. So what did this paper actually prove? Well, this paper, first of all, introduced a new concept, the concept of a trapped surface. And I guess we'll hear more about trapped surfaces in Annegret's talk, I think, which is next. So, for now, all we have to remember is it's some geometric thing, okay? And the point is that this notion of trapped surface, there exists such a thing in Oppenheimer-Snyder, in fact, in the region of Oppenheimer-Snyder, which is precisely Schwarzschild. So maybe I should have said this. It's not relevant so much for now, but possibly relevant later on, that somehow the region, the lighter shaded region of, you think this to be lighter shaded, I know the gray region, this diagram, is actually Schwarzschild in this picture. And the support of the star modeled by this pressureless fluid is here. So in any case, there are trapped surfaces in this spacetime, and in fact, sort of in the Schwarzschild region, there are trapped surfaces. Okay. Anyway, we'll hear more about what a trapped surface exactly is in the next talk, but it's some geometric thing. So this was a new concept introduced by Penrose, and then the only important thing, that's important about the definition of trapped surfaces is that it concerns something which is compact, and it's defined by certain geometric inequalities that are strict. So what that tells you is that, and here we see it in the words of Penrose, clearly trapped surfaces will still exist if the matter region has no sharp boundary or if spherical symmetry is dropped, provided that the deviations from the above situation are not too great. So that's just a fancy way of saying that Cauchy stability, if you take the evolutionary point of view, ensures that if you have a solution that has a trapped surface and you look at a solution that evolves from sufficiently close initial data, it will again have a trapped surface. Okay, so in particular, what I've drawn here is some perturbed spacetime, so spacetime that sort of arises from initial data sufficiently close to Oppenheimer-Snyder. And Cauchy stability, so the softest thing imaginable, tells you that whatever this looks like, who knows, but it will still have a trapped surface because Oppenheimer-Snyder did. So then Penrose's celebrated theorem says that under the above assumptions, so let me not state the most general form, let me just state the following corollary. For spacetimes solving, let's say, that system arising from suitably small perturbations of Oppenheimer-Snyder, then the spacetime is again future causally geodesically complete. So whatever happens, whatever this evolving spacetime looks like, who knows? One thing we do know is that there is still an observer like that green one, that's to say an observer who only lives for finite time. So this is historically known as Penrose singularity theorem, but it's better to call things by names that are not confusing. So it's preferable to refer to this as Penrose's incompleteness theorem, because that's exactly what it says. It says that under the above assumptions, spacetime is future causally geodesically incomplete. Okay. So there's something else about this singularity that we haven't yet discussed. Maybe the most famous thing, after all, about Oppenheimer-Snyder collapse, and that is that it's collapsed to a black hole. In particular, this singularity is actually inside a black hole, so it's cloaked by a so-called horizon. So you all remember how to read Dafermos diagrams. This is future null infinity. So this region here is the past of future null infinity. And by definition, a black hole region is the complement of that past. And the boundary of the black hole region is what we call the event horizon. Okay? So there's a sense in which the singularity is behind the event horizon. So it's inside the black hole region. So there's another way of thinking about what that means. That's to say, instead of sort of focusing on the horizon, you can focus on faraway observers. So this yellow observer here is a faraway observer, an observer, let's say, following a time-like geodesic, which never enters the black hole region. So the projection of such a geodesic Dafermos diagram is drawn for you here. And so the point is that such faraway observers, they live forever in this spacetime. So their proper time is infinite. Okay. So despite the fact that you have geodesic incompleteness, you have these good faraway observers that live forever. So there's actually a more convenient way of talking about faraway observers without sort of choosing particular ones and sort of splitting hairs about various, classes of observers. And that is looking at null infinity itself. So again, recall sort of the notion of null infinity. Well, originally it goes back to Penrose, and you can think of it as an idealization of faraway observers in the radiation zone. So strictly speaking, this is where gravitational radiation is measured. And there is a notion of completeness that you can define for null infinity itself. Okay, so anyway, I don't want to get into the details about how you formalize the completeness of null infinity. I mean, you can talk about an induced connection on null infinity and say that it's complete. Morally speaking, if you know what Eddington-Finkelstein or Bondi coordinates are, then with the usual normalization of the retarded time coordinate u, this is just the statement that the range of this u coordinate should go from -infinity to infinity. Okay. So that's what it means for null infinity complete. And you should think that morally, null infinity being complete is a substitute for talking about faraway observers living forever. Okay. So from now on, let's sort of banish faraway observers and just focus on null infinity being complete. That's really the statement. Faraway observers living forever. And I should mention that sort of this significance of the completeness of null infinity goes back to work of both Garrosh and Gary Horley. Okay, so this is clearly good, and in fact, I can't emphasize this more. That somehow, when Oppenheimer-Snyder spacetime first sort of appeared, it was thought to be a pathology, and very famously Einstein sort of repudiated that spacetime, and on the basis that this is the worst thing imaginable for a theory. You have singularities, you have whatever. Mind you, at that time, what the singularity was also the subject of confusion. But now, given Penrose's theorem, given the fact that this incompleteness is a stable property, then actually it's quite fortuitous that null infinity is complete. Okay, so it's quite fortuitous that, well, given that we know that there are going to be these incomplete observers, that sort of they somehow are hidden behind black holes, and null infinity is complete. So faraway observers still can observe forever. Okay, so this is actually really good. So despite the inevitability of geodesic completeness, the spacetime still enjoys a natural completeness property. So let's look now inside the black hole, and I want to turn to a paper which is not as famous as the ones I showed, but in some sense should be. This is a paper published in 1950 by J.L. Sink. So he was the first person. Actually, he was the first person to derive what's now often called the Kruskal extension of Schwarzschild, the maximal extension. But he was also the first person to utter the following words, at least in print, at least as far as I know. And again, I invite any historians of general relativity or any members of the audience to find an earlier reference to this kind of statement. So he says in that paper referring to the singularity of Schwarzschild, the singularity R equals 0 is space-like. So I think this is the first time that a singularity has been called of some causal character. But one might also want to look in the cosmological literature. Hans, looking at you. I searched, but I didn't find any such references, but it would be natural for this to also have been remarked. So the singularity R equals 0 is space-like. And moreover, he asks a very important question, namely, and again, this is all taken from this paper. The question may now be raised: is it conceivable that a test particle should travel right through the singularity R equals 0? And mind you, of course, he knew very well that the curvature, the Kretschmann scalar, blows up there. But he also knew very well that just because some curvature blows up doesn't mean that one should really think of this singularity as terminal. Okay? Because, well, we're all used to admitting certain kinds of singularities in our classical solutions of mathematical physics. Okay. So he asked this question. Now he thought that the answer was yes, but actually we now understand that the answer of this, in the case of this solution, is a definitive no, in the case of the Schwarzschild part. This was really first discussed in detail in the famous textbook Misner, Thorne, and Wheeler, chapter 32.6. What they showed, in some sense, is that if you have a stick figure observer, so you have an astrophysicist with arms and legs who's actually going along that trajectory, then you also have to keep in mind the Jacobi equation, because arms and legs, we all know, are Jacobi fields, right? Arms and legs are. So they propagate via the Jacobi equation, and so, well, what happens to them, depending on their orientation, is that they get infinitely stretched or compressed. Okay, so here we see the fate of this observer. Okay, so the astrophysicist in the limit r goes to 0 is crushed to 0 volume and indefinitely extended length. Great. So again, it's sort of inconvenient in discussing these issues to have to talk about observers, because then you have to think which observers, which do etc. So there's a dual way of thinking about this, which is don't think about observers, just think about the metric and try to, in terms of the metric, understand, what singularity of the metric does this correspond to? Does this phenomenon correspond to, that sort of observers get infinitely distorted in the manner I said? And keep in mind, this is not curvature blow-up per se. So curvature blow-up, it's easy to convince yourself, is not enough to assure that observers get infinitely distorted, because if you remember the Jacobi equation, you have to integrate curvature back twice. Okay, so pointwise blow-up of curvature is clearly not sufficient. So actually what turns out to be the right notion as far as sort of metric singularity to really capture this property that singularity destroys observer is inextendability of the metric as a continuous Lorentzian metric. And so this property, even just this property of the Schwarzschild spacetime, was first proven only recently by Jan Birsky in this modern classic of differential geometry. Okay, so actually, maybe strictly speaking, he is only proving the inextendibility of the Schwarzschild part. So I don't know, has the inextendibility of Oppenheimer-Snyder actually been proven? Okay, so there's still something to do even here. Okay, but in any case, at the level of this talk, I'll have to bend the truth at some point. So Jan, please don't keep me too honest. You can keep me honest, but not too honest. Okay. All right. I should actually say something about the history of this problem. So this fact was actually first asserted in Hawking and Ellis in this phrase here, but and this was I guess an exercise in our lecture notes with Igor Rodnyansky, but it turned out that the exercise needed a longer paper. Okay. All right. So okay. So that's the statement about Schwarzschild. So now let me make a claim to you that just like the completeness of null infinity was good, this property of Schwarzschild, we should also think of this, or Oppenheimer-Snyder, if you will, we should also think of this as good. So maybe this is less obvious why we should think about this as good, but it's important to understand this in order to understand the sort of ideology behind the cosmic censorship conjectures. Of course, you see, having complete null infinity, that's clearly good. You know, observers, faraway observers living forever, that's clearly a good thing. Why is it good that these observers get destroyed, get torn apart by infinite tidal deformation? Well, it's good because it provides what I would call an attractive epistemological closure to classical general relativity, despite the presence of singularities. So what does that mean? Well, that means the following: that classical observers, they either live forever in a space-time determined classically by initial data, or else they are destroyed as classical observers. So the point about this is that either way, classical theory answers uniquely all classical questions about classical observers. Because you see, the classical observer which is destroyed, well, maybe after the observer is destroyed, if you're really, quote, at the singularity, you can start saying the usual words that, you know, some other theory, some quantum gravity should sort of take over, which very well may be the case. But by that time, the classical observer will no longer be a classical observer. This classical observer will have been destroyed, will be some quantum soup, and it's not surprising that we need the quantum theory to talk about the quantum soup. The danger is if you have incomplete classical observers that remain classical until the final moment where the theory no longer says what happens. Okay. So you should think that really remarkably, in this sort of most basic first example of gravitational collapse, you have this epistemological paradise. Okay, that given that there are singularities, it's as good as it gets from this point of view, and it's really a remarkable feature of singularity in general relativity. Okay, so that's Oppenheimer-Snyder, and you should think that cosmic censorship conjectures is all about preserving all that's good in Oppenheimer-Snyder. Okay, so if you will, briefly, cosmic censorship conjectures hypothesize that the good properties of Oppenheimer-Snyder always hold, or at least hold generic. Okay. So let me talk about that. So in order to talk about the formulations, let me remind you fundamental theorem in the subject that, okay, in order to discuss rationally any problem about dynamics, we have to pay tribute to, and this is the celebrated theorem of Yvonne Choquet-Briard, and well, together with its maximalization, which she proved. So her original theorem was actually 1952, but maximalization, which will be relevant here, was proven with Bob Garrosh in 69. So this is just a theorem that says that for every sufficiently regular initial data set, for the vacuum Einstein equations, or your favorite reasonable Einstein-Mather system, then there's a unique maximum development. There's sort of this unique space-time, which is globally hyperbolic and solves the equations of motion and admits as a Cauchy hypersurface the given data. Okay, so this we already in some sense saw this in the context of Oppenheimer-Snyder. That space-time that I was drawing all this time was the unique Cauchy development of this impeccable initial data that I talked about at the very beginning. Okay, so this notion is fundamental, and in fact, maybe I should also mention that famously, Jan Zbierski desornified this construction for his previous work. Okay, So now let's recall Oppenheimer-Snyder. So remember, what were the good properties of the sort of the singularity? So one of the good properties was that it was cloaked by a horizon. That's to say, it was inside the black hole region. So here we come to weak cosmic censorship. So this was first discussed in this famous paper of Roger Penrose from 1969. So he writes here, we are thus presented with what is perhaps the most fundamental unanswered question of general relativistic collapse theory, namely, does there exist a cosmic censor who forbids the appearance of naked singularities, that's to say, singularities that are not clothed by a horizon? Okay, so all right, so these were the original words where cosmic censorship was first discussed. But as I remarked earlier, there's sort of another way of thinking about this, and that is, instead of focusing on the horizon per se, focusing on null infinity. Because remember, I discussed previously that, well, you also have these good observers, precisely the observers that don't fall into the black hole, that live forever. And well, instead of thinking of the observers that live forever, you can also think about null infinity itself, and null infinity is complete. So somehow, if you want, instead of focusing on the horizon itself, you can also say that what's good about this singularity is that even though you have a singularity, null infinity is still complete. So this sort of focusing on null infinity is actually convenient, and this was first really attempted by Gary Horowitz in what I think was his thesis under Bob Garrosh at the University of Chicago, because to talk about the completeness of null infinity, you don't have to ever mention singularity per se. And well, we all know in general relativity, defining singularity, etc., sort of locating a singularity can be tricky in full generality. So in view of this, sort of the modern formulation of what we call weak cosmic censorship, and this goes back to Garrosh, but I'll take the formulation from this this paper of Christodoulou from around the turn of this century. I really recommend this paper for anyone who wants to learn about this field. So the modern formulation is actually the following: generic asymptotically flat initial data have a maximum future Cauchy development possessing a complete future null infinity. Okay. So I hope this doesn't, to the experts, sound like a bait and switch. It's not meant to be. It's simply, this is supposed to be the statement that generically singularities, if they exist, are cloaked by horizons. But in some sense, okay, it's not the cloaking by the horizon per se that we necessarily care about, because we're not going to visit the horizon. Okay, what we care about is that there are the observers outside the horizon who live forever. So, okay, you can actually even forget about the horizon if you want in the statement and just focus on the observers who the existence of observers who live forever. And the correct way to formalize that is having a complete null infinity. Okay, so so this you really can think of as actually the weakest possible weak cosmic censorship statement, but this statement has sort of taken hold, and let's say this is a convenient sort of statement to have in mind. Okay, so so one thing that maybe I should point out is the presence of the word generic here, and it's not a priori maybe clear why you should have the word generic, and I'll get back to that later on. Okay. So okay, so that's the first of the cosmic censorship conjectures. So what about the second of the conjectures? Well, so let's go back to the paper of Jan Spirsky. So this is taken from the paper of Jan Spirsky. So remember, the good thing about the structure of the singularity itself inside the black hole was its strength, was the fact that it was very strong, and well, the way to understand its strength without talking about individual observers is that the metric was inextendable, even just as a Lorentzian manifold with continuous metric. So, so somehow you should think that strong cosmic censorship is supposed to be the hypothesis that generically this should be true. Generically this should be true. Okay, so again, this comes originally from a slightly later paper of Penrose from 1974, gravitational collapse, and this terminology is all due to Penrose. And so the modern sort of evolutionary formulation of this conjecture is that generic asymptotically flat initial data should have a maximal future development, which is locally inextendable. So this just says that the boundary of spacetime should be locally singular in some sense. And then you have to fill in as what? And well, motivated by what's true in Schwarzschild, and motivated by the fact that ideally we would like to have the same epistemological closure that we had in Oppenheimer-Snyder. You could say these words as Lorentzian manifold in a continuous manner. Okay, so this is exactly the formulation as taken from this paper from around 2000 by Stozel. Okay, so very good. Okay, so this is what I'll call the continuous formulation of strong cosmic censorship. All right, so so this is great. There's one other good property of Oppenheimer-Snyder that I want to recall, namely the property which was pointed out already by Singh, namely that singularity is space-like. So sometimes strong cosmic censorship is confused with the conjecture that generically singularities should be space-like. Okay, so very often you see this. In fact, I've taken this from slides of Roger Penrose, and he formulates it like this. And of course, okay, I mean, it's his conjecture originally, so he cannot be accused of being confused. But for our sake, it's good to have separate names for separate conjectures. So I'm going to give a separate name for this conjecture, namely the conjecture that generically singularities are space-like, and I'll call it the space-like singularity. Space-like singularities conjecture. So generic asymptotically flat initial data have a maximal future development whose finite future boundary is everywhere space-like. Now, there are various issues with this conjecture. One being that maybe it's not exactly clear how to define the finite future boundary. Specialists in Lorentzian geometry here, of which there are several, maybe can tell me whether you believe there is a good formulation in principle of such a statement. I might make one comment. You might say, what is the relation of this statement to the other statement? Well, so if in some sense the finite future boundary is space-like, then it should be locally inextendable there, at least as something. Okay. That's to say, if you have a regular Cauchy horizon, we're going to see this example later on. If you have a regular Cauchy horizon, that Cauchy horizon has to be null. So if there is an extension of spacetime, at least in a sufficiently regular class, then the boundary of spacetime has to be null there. So in some sense, the finite boundary being everywhere space-like, you can think is somehow related to local inextendability. But okay, that's really the only connection between those two statements. And in some sense, it's really the inextendability which has more direct epistemological relevance in giving closure to the theory. But the space-likeness per se is also an interesting property and related possibly in terms of. Okay, so this is the space-like singularity conjecture. Okay, so many of you probably know in the audience that actually the last two conjectures that I stated are actually false. So this follows from a theorem with Jonathan Luke, which is now several years old. So basically in this theorem, we proved that any vacuum spacetime which polynomially settles down to a subextremal Kerr along its event horizon will have a non-empty piece of Cauchy horizon, CH plus, across which the metric extends continuously. So, as a corollary of this, in particular, if you think in the language of observers, this means that any observer falling into such a space-time, exactly because of the C0 extendability, okay, then the observer actually survives the plummet sort of into the black hole through the Cauchy horizon. Okay. All right. So, so as a corollary, both the C0 formulation of strong cosmic censorship and the space-like singularity conjecture, as I stated them, are actually false. So we should go back to the drawing board before we finish this discussion of the formulations of cosmic censorship. So why did one ever believe that these conjectures should be true in the first place? Because, of course, exact Kerr spacetime, okay, is exactly an example of a spacetime that satisfies Penrose's incompleteness theorem on the basis of having a extendable maximal Cauchy development, in fact, extendable so that every incomplete observer lives another day in the extension. So, so why did one ever conjecture these in the first place? Well, remember the conjecture here always had the word generic. So what was the role of genericity? Well, the conjecture was based on the so-called the so-called blue shift instability, and this is again one of the remarkable discoveries of Roger Penrose, first discussed in this paper here in print. So you all know the blue shift. You have these two observers. This observer is one of the lucky ones who lives forever, stays out of the black hole. This is an observer that falls into the black hole and in finite proper time reaches this Cauchy horizon here. So if this observer sends a signal at a constant rate to the other observer, then of course this signal is infinitely blue shift. Okay, this is just because this time is infinite, this time is finite, and you might think that, well, this all describes in the geometric optics limits some behavior for the Einstein equations themselves. So this should be measured as some sort of instability at the Cauchy horizon. And while the original expectation of Penrose was that this instability at the nonlinear level should be so strong to actually destroy completely the Cauchy horizon and replace it by a space-like singularity. So this was the original motivation for hoping that strong cosmic censorship is true. Now, our theorem, Jonathan says that, well, that doesn't happen, but of course there is still this blue shift, and in particular there is still this blue shift on the spacetimes that we ourselves discuss. So if you sort of look heuristically more carefully at this calculation, then you can make a precise prediction for generically how singular this Cauchy horizon should be. And this leads to a revised formulation of strong cosmic censorship, which was again made by Stolhulu and appears in print in his celebrated book on formation of black holes in general relativity. Remember, this was the original formulation of Christodoulou. So the point is that what you should add here is that the spacetime should be locally inexpandable as a Lorentzian manifold with continuous metric, such that moreover the Christoffel symbols are locally square integer. So this is suggested by that this is true is suggested by the details of this blue shift calculation. Why is this of potential physical relevance? Well, this is exactly the threshold for at least the naive notion of a weak solution of the Einstein equations. So what this would tell you is that there is no extension of spacetime satisfying the Einstein equations even weakly. So in this sense, even any notion of classical solution, where by classical solution, this is slightly confusing, maybe terminology. So because sometimes we distinguish between classical and weak solutions, but any reasonable notion of the of the non-quantum equation, whatever you want to call that, itself breaks down. So in that sense, you still have some sort of determinism. Okay. Of course, you really have to wonder: is it determinism because I say I exclude any other solution? That's sort of determinism by fiat. It is still a little bit philosophically unsettling because it's not clear that this truly gets observers out of the classical domain. But in any case, it is what it is, and this is the best that we may have. So maybe we should learn to love it if it's true. Okay. So this is the revised formulation of strong cosmic censorship. So what about the space-like singularity conjecture? Well, a revised conjecture is so this was the original conjecture, the generic asymptotically flat initial data of a maximum future development whose finite future boundaries everywhere space-like. Again, this is not true. So a revised conjecture is that there exists an open set in moduli space of asymptotically flat initial data, such that the maximum future development has a piece of space-like singular boundary. And it's quite remarkable that even this statement is completely open. That's to say, even the statement that not generic, that there's some open set somewhere in moduli space such that some piece of the singular boundary is space-like. This is completely open. So let me call this the revised space-like singularity conjecture. You can actually make a more ambitious conjecture, which is that for generic asymptotically flat initial data, conditioned on the space-time being geodesically incomplete, and conditioned on there being one asymptotically flat end, which is, of course, the physical appropriate assumption in the context of gravitational collapse, then there should be a piece of the space-like, the piece of the singular boundary is space-like. So that's the conjecture, if you will, that sort of gravitational collapse, if it forms a black hole, the Penrose diagram should look something like this. So I'm not going to talk more about this conjecture, but I'll refer you to the talk of Maxime Van de Mortel, because Maxime has maybe the most promising work in the direction of this conjecture. In fact, sort of has essentially a resolution of this in a strictly symmetric model. Okay. But as I said earlier, I'm not going to pay justice to some of the most interesting things here, especially things that will be talked about in other talks. Okay. And speaking of that, I've in this whole discussion of cosmic censorship, I've really focused on gravitational collapse, and I haven't discussed at all these problems in the context of cosmology, okay? And in various, let's say, non-asymptotically flat cases, where there's a big body of work, and in fact, there's a strong relation of these issues that we've discussed many times with some of the participants here. So, but again, I apologize for not saying more, but we'll hear about issues related to this in any case in the talks of Hans Ringström and Grigorios Fournodavlos. So I defer to them. Okay, so this is what I want to say about the cosmic censorship conjectures per se. So in the rest of the talk, I'm going to just I won't give a actual discussion of the complete status of these conjectures, but I want to discuss essentially two things. So, and the first thing will be Christodoulou's scalar field model, which is a reference point, I think, for any discussion, and something that maybe students in the audience who might not know these old papers, I really recommend learning this. And already there'll be several open problems connected to this model, and then something else at the end. Okay, so let's begin with Christodoulou's model. So his model is a model of a strictly symmetric self-gravitating scalar field. So let me just make some comments about the motivation for this model, which is important to have in mind. So actually, this was not the first model that Christodoulou considered when he was trying to mathematically understand cosmic censorship. The first model that he considered was actually sort of the Einstein-Euler in the pressureless case, so the same thing as Oppenheimer-Snyder, but dropping the homogeneity. So actually, in the Oppenheimer-Snyder model, not only is this spherically symmetric dust collapse, but the star is actually homogeneous. So it's a very, very special. So he wrote various papers about that model. I don't want to get into the details there, but somehow the problem with dust models is that dust is a very poorly behaved matter model. So you can use it, you can prove things about it, but it forms on its own various sort of nasty singularities. In fact, how to understand those singularities is not completely understood, even for that model. So anyway, that's also a very interesting thing, but in some sense, it's actually harder to interpret any result that you have for that. So what Christodoulou was looking for was, in essence, a replacement for vacuum in spherical symmetry. So we all know Birkhoff's theorem, which says that in spherical symmetry, there's no non-trivial vacuum dynamics. On the other hand, certainly spherically symmetric analysis is much easier than analysis beyond spherical symmetry. So what he was looking for was a matter model for which essentially you don't have new features of the matter that aren't sort of indicative of vacuum in 3+1 dimensions, but you have the advantage of spherical symmetry. So it was exactly these considerations that led him to the Einstein scalar field model, which is these equations that you see here under spherical symmetry. So you should always remember this, that this analysis is not because one takes this matter model seriously as a matter model, that one really thinks about the matter this represents. Although, well, you can think of this as a hard equation of state, maybe in the interior of a neutron star, maybe Franz knows more about this than I do, so I shouldn't say anything lest I embarrass myself. But in our context, you really should think of this as a poor man's vacuum. So his first contribution, major contribution for this model was his proof of the examples of naked singularity formation for this model. So this was appeared in the paper I just flashed by you. So the theorem is the following. There exist regular asymptotically flat initial data evolving to spacetimes having the following Penrose diagram. So there are examples that have this, there are examples that have that. So this is a naked singularity, okay? This is a singularity which is not inside the black hole region. And this is what I'll call a locally naked singularity. So see, in the first case, null infinity is incomplete. I have to tell you that, by the way, you can't actually read that off from the diagram, but it's claimed that that's part of the example. Well, in the second case, null infinity is actually complete, okay? But in both cases, this part of the boundary is null, and in both cases, the spacetime is regularly extendable to a larger spacetime beyond a Cauchy horizon. Okay? And I put this paper here to pay homage to the fact that this terminology, Cauchy horizon, which is now completely standard, is again one of the contributions of Stephen Hawking. Okay, so so what you're supposed to remember in particular is that in these examples, besides the question of the incompleteness of null infinity, there are observers who pass into the extension, which is not uniquely determined by initial data. But in the second example, faraway observers, they do live forever. So you should think that this example is, were it generic, would be incompatible with both weak and strong cosmic censorship. This example would be incompatible with strong cosmic censorship, but compatible with weak cosmic censorship. Okay. All right. So it's in the first case what we refer to as a naked singularity, and maybe I'll call the second one a locally naked. And this is just what I just said, that the first case violates in quotations, because of course these are conjectures about generic solutions. Weak cosmic censorship, and the second and both examples violate strong cosmic. Okay. And I should say here that additional examples of negative singularities were also produced by numerical simulations of Chubbutuik, and I'll get back to this issue in just a second. All right. So this is the first thing. And if you want, it's these examples that really said that you need generic in the formulation of weak cosmic censorship. And it really wasn't clear that you should need genericity in the formulation of that for a reasonable matter model. Certainly for unreasonable matter models, there were examples of naked singularities. There were in fact examples of naked singularities that appeared to be generic, but that you would need genericity for a reasonable matter model. These were really the first examples that sort of suggested. Okay. So again, I don't want to talk about this more here because I understand it will be talked about later, but very important contribution of the last few years in this subject was showing that, well, you can forget, you know, is this matter model reasonable? Is that matter model reasonable? We now have vacuum naked singularities. So these were produced by Igor and Yakov Schlappenthal-Rothman and also a single author paper by Schlappenthal-Rothman in the last few years. So you can think of this as a major generalization of the work of Christodoulou of tremendous complexity. And I guess we'll hear more about this in Yakov's. You are talking about this, right? Good. Okay. So naked singularities exist. They're out there. And you'll hear more details later in the conference. But the good news is that in the spherically symmetric model of Christodoulou, they're unstable. And in fact, all the original versions of all those conjectures that I gave are true, reduced to spherical symmetry in that model. So this is a result of this remarkable paper from 5 years ago. So the theorem is the following: for generic as regular asymptotically flat initial data, the corresponding spacetime has one of the following Penrose diagrams. Either you disperse, so this is the Penrose diagram of Minkowski space that we know and love, or you form a black hole, and this is exactly the Penrose diagram of Oppenheimer's line. So generically, the above examples notwithstanding, it's either this or that. So in particular, in both cases, null infinity is complete. So weak cosmic censorship check. And in both cases, the spacetime is inextendable, in principle as a manifold with continuous symmetry. So it's certainly, well, anyway, ask Jan for more details there. Okay. So thus, both weak cosmic censorship and strong cosmic censorship, as well as the space-like singularity conjecture, because certainly by this Penrose, well, if you believe my statement, then that's certainly space-like. So all the original formulations are actually true. Restricted, of course, to this model, restricted to spherical symmetry. Okay. So let me just say few words about the proof, and this is a very superficial discussion of the proof, but it's actually useful maybe to keep in mind because it will be related to the discussion we'll have after. So the proof relies actually on the following insight. So imagine you have a first singularity. First singularities in this model, they only happen on the center. So imagine you have first singularity. Okay, a priori, you don't know. Maybe there's a Cauchy horizon, maybe there's a space-like singularity. So what you can show is that there's a dimensionless quantity 2m on R, which is greater than some epsilon. Okay, so there has to be this concentration at that point. Okay, so from this you can actually show that radiation falling parallel to the past light cone of P is infinitely blue shift. So there's a sort of geometric blue shift effect associated to this. So that blue shift effect of Penrose, it actually also shows up here. And this is non-obvious case. So generically, unless there's some cancellation, this actually focuses radiation to form trapped surfaces. In fact, trapped surfaces arbitrarily close to P. And then because of the details of this model, once you have those trapped surfaces, then it follows that you'll have actually a space-like singularity that goes like this. So that's the proof. And almost as an afterthought, once you have a trapped surface, then null infinity is certainly complete. Okay, so simple as that. All right. So what I want to compare actually is with the picture of critical collapse and the work of Cheptuik, and this is maybe more sort of for the experts. So what I meant to draw here is a picture of moduli space. Okay, and many of you might be familiar with these pictures. So this is the trivial, let's say, Minkowski space's solution of this model. And actually, Christodoulou, in an earlier paper on this model, he showed that that was stable. Okay, so there's a neighborhood in moduli space of dispersive solutions. On the other hand, somehow you can consider the black holes. There are black hole solutions. It's easy to construct an example of a black hole solution in this model. So what you might try to do is take a one-parameter family that interpolates between Minkowski space and the black hole solution. And I don't know, actually it's interesting. This model, if you have a black hole solution, then any perturbation will be a black hole solution. That's easy to show. So you can look at the first thing going this way that isn't a black hole solution. Okay, and you can ask, what is this? Well, this is exactly what Cheptuik did famously numerically. And what he found is these to be naked singularities. And moreover, even more surprising, he found that there was critical behavior associated to this threshold, which maybe I won't discuss the details of. Okay, so one thing that I want to stress is that Christodoulou's naked singularities are not these ones. They're somewhere here. His examples. All right, so let me end this part with some open questions about Christodoulou's model, and because there are many young people in the audience, these are great questions to think about. So the first is related to what I just said. Do naked singularities indeed occur at the threshold of black hole formation? And do all such threshold spacetimes contain naked singularities? Now, there's a very interesting paper of Jonathan Luke and Sunjin Oh, which basically says that, well, applied to this problem, that if you have a threshold solution, either it's a naked singularity or it's a solution that disperses but doesn't disperse quite fast enough. Hope I'm quoting it sufficiently accurately for the general level of accuracy of this talk. So it might be interesting to know, do there exist such funny sort of solutions that disperse but not too well, or are all threshold solutions naked singularities? Now, another thing which I completely swept under the rug, and maybe Yakov will also discuss it more in the context of his talk. So actually, those naked singularities, they arise from regular data, and that was the word I used, but I never told you how regular. And it turns out that the data is regular in the sense that it's in a well-posed class, but it's not smooth, it's not C infinity. And the whole mechanism, both of the construction of the examples of naked singularity and for the instability of naked singularity, they both rest on this slight lack of regularity. So do naked singularities occur from smooth data? Particularly if you think about that picture of moduli space, well, that picture should be the same in any regularity class, right? So somehow, if you believe that naked singularities occur as a threshold behavior, then you should think that in any class, regularity class in which it makes sense to interpolate, you should be able to have naked singularity. So this may be related to the previous. And as I said, the genericity class, so if you paid attention to that proof, having some things propagating on that backwards null cone, very weak singularities propagating on that backwards null cone is essential to the proof. So the proof really exploits a slight lack of smoothness of the data. So can genericity be proven in a more regular class, or maybe, I don't know. So these are all important questions. And maybe let me say one final question about this, which doesn't have to do with nakedness per se. So the space-like singularities that we saw in that class, are they locally stable generically? Are they locally stable? So there's some very interesting work of Warren Lee, and this is also related to what I understand Spiros Alexakis to talk about in his talk. Okay. All right. So in the last 5 minutes, let me talk about my final topic, which is often not discussed in this context, but I think it will be interesting to do so, which is the question of overcharging, naked singularities, and the third law. So what is this about? So one aspect of Christodoulou's model is that it doesn't have charge. And well, because it doesn't have charge, it doesn't have, let's say, Reisner-Nordstrom type behavior in spherical symmetry. Okay. And well, we all know that charge in spherical symmetry, you can think of it also as a poor man's angular momentum. Okay. So in particular, if you want the global Cauchy horizons that you have, say, in Kerr in spherical symmetry, well, you have them in the Reisner-Nordstroms. So let's remember the Reisner-Nordstrom family. So I've drawn the Penrose diagrams of the Reisner-Nordstrom family. This is subextremal Reisner-Nordstrom solution. You see here the global Cauchy horizon. If you think of this as, let's say, a Cauchy hypersurface. And most of us know that we also have extremal Reisner-Nordstrom. So this is its Penrose diagram. Here you see that, well, anyway, it's the picture. And finally, a super extremal Reisner-Nordstrom. So this is the picture. So stole these pictures from in Unger. Sorry about that. Lazy to draw Penrose diagrams after my very nice time at the whiskey bar last year. Okay, so this is the Reisner-Nordstrom family, and if you notice in super extremal Reisner-Nordstrom, this is actually singular. So this looks like the Penrose diagram in Minkowski space, but don't fool yourself. This is a singularity. Okay, so in particular, this is a naked singularity, but of course, if I try to draw a Cauchy hypersurface here, it's not complete. Okay, so this is a naked singularity, but it doesn't manifestly arise from initial data. So what you might ask yourself is whether you can create a naked singularity from initial data by, starting with something that looks like this and throwing charge into it so that it becomes extremal. And then, it becomes super extremal, and this has a naked singularity. So is there a way to create a naked singularity by overcharging subextremal Reisner-Nordstrom, or a collapsing spacetime to subextremal Reisner-Nordstrom? So this is an old story in the subject. Now, of course, to study it, let's say dynamically, you need to replace Christodoulou's model of Einstein's scalar field with a model that allows for you to have charged matter. So the model to have in mind is the model of a spherically symmetric charged scalar field. So now I've given the scalar field a charge, I've made it complex, and I've coupled in the Maxwell. And well, I also need to have the equations of motion for the scalar field and the Maxwell equations, but I've omitted them here. Okay, so this is sort of a model where you can try to understand, is it possible to, to supercharge a black hole and create a naked singularity? Okay, great. So at this point, I want to bring in what's called the third law of black hole thermodynamics. This goes back to this paper of Bardeen, Carter, and Hawking, the 4 laws of black hole mechanics. Well, the reason that I want to bring this up is the following. So the third law of black hole thermodynamics is the statement that you cannot, in finite advanced time, create an exactly extremal black hole. So in the charged case, so an exactly extremal charged black hole. So what they write in this paper, so this paper is where this was first formulated, is the following words. Another reason for believing the third law is that if one could reduce kappa here is the surface gravity, kappa is equal to 0 is precisely the extremal case. If one could reduce kappa to 0 by a finite sequence of operations, then presumably one could carry the process further, thereby creating a naked singularity. If this were to happen, there would be a breakdown in the assumption of asymptotic reduction. So now it continues with why naked singularities are. So, so the reason that I bring this up and its possible relation to violation of cosmic censorship. So the question of whether the third law is a cosmic censor, if you will, is that this third law of black hole thermodynamics is actually false. So this was recently proven in this very nice paper of Kayla and Unger. In fact, what they showed is that there exist spacetimes that solve the equations that I wrote down before, whose Penrose diagram looks like this. So in particular, there's a era where you have a sub-extremal apparent horizon, and then at finite advanced time, the solution becomes exactly extremal isotropic. And the reason I bring this up, apart from its interest in of itself, which I don't want to discuss further, is that you might get worried if you know the literature that the failure of the third law could mean that cosmic censorship, weak cosmic censorship, is false. Because after all, the motivation for the third law, or one of them, besides the analogy with classical thermodynamics, was that the third law could be our cosmic censor, or one of our cosmic censors. So what I want to assure you is that all is still well as far as the weak cosmic censorship, despite this. And indeed, in this paper of Komemi, it's proven that irrespectively of whether you can violate the third law, the paper does not address that. Anytime you have let's say a non-empty apparent horizon, then you never have naked singularities in this model. So whatever overcharging means, whatever it's supposed to be, it can never create a naked singularity. Okay. So all right. So maybe I'll end with one last slide and say the following words. So how should one understand extremal black holes, and what is the possible relation, true relation, to the problem of weak cosmic censorship? So the picture that comes out of the work of Kayla and Unger is that one should understand extremal black holes as a threshold phenomenon, not dissimilar to the threshold that I discussed previously of critical collapse. So remember, critical collapse, this was this picture here, the dispersive solutions, the black hole solutions, and you have this threshold of presumably naked singularities that was seen numerically by Treptowick, on which you also have critical behavior. So, so when you add charge to the model, you might expect the sort of picture of moduli space to look something like this. And I purposely have done it like this because, you know, who knows what other monsters are and how regions connect. So I've zoomed in. So again, of course, you have the trivial solution and a dispersive region around it, presumably, again, bounded by naked singularities that are a threshold to black hole formation. But deep inside the black hole region, you can have extremal black holes. They can even form exactly extremal in finite time. That's the theorem of Kayla and Unger, but more generally, you can have asymptotically extremal black holes. And you can think that these can be a threshold to another component, maybe it's connected with this, maybe it's not, of the dispersive regions, or maybe more generally, solutions that disperse a bit later, but potentially solutions that, solutions that don't disperse until a bit later, but potentially completely dispersive solutions. Let me draw this picture like that. So you really should think of extremal black holes as this sort of threshold behavior, and I think it would be very interesting to probe that further. Let me just say the following words. So this threshold is further complicated because the generic spacetime on this boundary, Unger and Kayla, of course, constructed a very special one. The generic one on this boundary will also be subject to the Aretakis instability. Okay? So the generic spacetime on this boundary may look sort of funny, but it might be asymptotically extremal in a certain way. So for more details, you can look at a conjecture 4.2, if I'm quoting it right, that we made with Holzigel, Rodniansky, and Martin Taylor. And I should say that the sort of super rotating threshold, so the analog of this whole story where I replace Rice and Nordstrom with Kerr, is subject to even stronger instabilities. And this, for this, I relate you to the recent work of Geich. So in particular, in the sort of super rotating threshold, because of these stronger instabilities, you might still wonder whether there is a window for naked singularities near this threshold. Of course, now naked singularities that have nothing to do with the naked singularity of extremal Kerr, but have to do with sort of the long time behavior of these sort of funny singular behaviors. And you might even wonder whether such naked singularities, if they exist, we have no idea what they look like. So they may, our intuition from the spherically symmetric examples may be inappropriate. We might even wonder, could such naked singularities even be stable? So maybe here is a window, a very different window of trying to violate weak cosmic censorship, but if so, a very subtle one. Okay, so sorry to go a little bit over. Thank you.